Yes. So this set of differential equations needs to be solved using the matrix method, yeah? And the way we can do this is we can set up the matrix in the form of x equals a lambda, or x equals a1, whatever it is. These are all matrices. Yeah? So we get x prime, y prime to equal 1, 1, which are the coefficients of the corresponding letters, yeah? 4, 1 times xy. So we're just putting the system of equations in the form of a matrix. This is our A matrix. So we're going to go and do, to find the eigenvalues, we will say the determinant of A minus I lambda has to equal 0, where our lambdas are the eigenvalues. Where our lambdas are the eigenvalues. Yeah? So A will be 1, 1, 4, 1. I is the identity matrix. So that's lambda times the identity matrix. The identity matrix is a matrix with 1 in the on the diagonals and zeros everywhere else. And when we're done, we're going to take the determinant of this full matrix and set it equals 0. And so we get 1, 1, 4, 1 minus lambda is a scalar, so we can multiply it by each one of the components of our matrix. So we get lambda 0, 0 lambda. And when we're done, we will take the determinant of this and set it equals 0. And now we can subtract from each other. So we get 1 minus lambda, 1, 4, 1 minus lambda. And we're going to take the determinant of this matrix and set it equal 0. Now you remember how to take the determinants, yeah? Yeah. So the determinant is we crisscross. So the determinant will be 1 minus lambda squared, because it's 1 minus lambda times 1 minus lambda, minus 4 equals 0. So we don't have to FOIL this. We can just solve it as is. Minus lambda is equal to plus or minus 2. So that means lambda, or 1 minus lambda is equal to 2, which makes lambda equal minus 1. So that's one eigenvalue. Or 1 minus lambda equal minus 2, which makes lambda 3. And that's the second eigenvalue. And now we're going to go after the eigenvectors. Okay, so you're going to take your eigenvalues and plug them into your A matrix. Or, sorry, not the A matrix, the matrix that you got here from the determinant of A minus I lambda.
Oh, yeah, plug it back into this.
Right. So let's start with lambda equal minus 1. And so we're going to get 1 minus minus 1 becomes a 2. 2. And we're going to consider our first eigenvector to be u1, v1. And we're going to set this equal to 0, 0. Now, we're going to get two equations here, are we not? So we're going to get 2u1 plus v1 equals 0, and 4 u1 plus 2v1 equals 0. Now, those are linearly dependent set of system of equations. You can't solve them because if you multiply the first equation, so we do not attempt to solve the system of equations. Instead, what we do, we take one of them, we solve it in terms of the other. We assign a value for one, and we find the next based on the assumption. So now our eigenvector will be if u1 is 1, v1 is minus 2. u1 to be 1, I plugged it into this equation and I solved for v1. So this is my eigenvector for eigenvalue lambda equal minus 1. Now we're the second. Eigenvalue. So now we're going to do lambda equals 3. And we're going to plug it into our matrix. So we get 1 minus 3. We're going to plug it in matrix star. We called it matrix star. So 1 minus 3 is minus 2. 1. 1 minus 3 is minus 2. Okay. Okay. And now we're going to multiply it by our second eigenvector. Let's call it u2, v2. And we're going to set this equal to 0, 0. And again, we're going to get two sets of equations. Minus 2 u2 plus v2 equals 0. And 4 u2 minus 2 v2 equals 0. Again, those are linearly dependent set of equations. If you multiply the first one by negative 2, you get the second one. Or if you divide the second one by negative 2, you get the first one. We do not attempt to solve these two equations. Instead, we take one of them, we assign a value for one of them. Let's say u2 equals 1, so v2 will equal 2. And therefore, our second eigenvector will be what? Will be u2, v2, so 1, 2, for eigenvalue lambda equals 3. Now we can move on to write the solution of our differential equation. based on these eigenvalues and eigenvectors. So x, y will equal to C1e. Now the eigenvalues correspond to the exponentials on the solutions. So the first one was -1, so this will be minus t multiplied by the first eigenvector, which was what? 1 minus 2. No, 1 minus 2. Plus, now the second, C2e. Again, this is 3 is the exponent of the exponential, so this is 3t multiplied by our second eigenvector, which is 1, 2. Now you may wonder, how come there's 2? Because there's 2 different differential equations. Solutions, yeah, there's x and y. The individual solutions for these differential equations go in a matrix format, kind of swap across the aisle. E to the minus t times 1 is C1e to the minus t. C2e to the 3t times 1 is C2e to the 3t. Right? And the second one, y equals, now C1e to the minus t times negative 2 will be negative 2 C1e to 2 times C2e to the 3t will just be 2 C2e to the 3t. Now, of course, the final answer. These are the solutions for the 2 differential equations using the matrix method through Eigen. Keep in mind that those eigenvectors that I found are not unique, because you could have chosen signing 1 for u1. You could have said, I'm going to let u1 equals 17.7. And then v1 will be minus 2 times 17.7. And here, for eigenvector number 2, I assigned u2 to be 1. You could have said, I'm going to let u to be 7.895356817. And when you find v2, it will be according to that. But of course, the objective is to pick simple numbers. Because the whole idea behind this is, figuring out an easy method with keeping the algebra fairly straightforward. Now, this concludes this question for when values are distinct, real. There's 2 other cases when they're repeating and complex. So this was the method, this was the way, one case when they're real. So now you can attempt the second one yourself, no? Did you do this one? You have questions on it?